Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so our next talk will be given by Francois Moran from the École Polytechnique in France. Francois is well known for his work on the elliptic curve primality proving algorithm and has held many world records, probably still does. And today he will speak to us on elliptic curves with complex multiplication, history, and computations.
Okay. Thank you, Christine. So thank you for inviting me. Thank you for putting my talk in a decent time period because, as you can imagine, we are all jet lagged. And so just after my talk, probably I will go to sleep and so on and so on. So welcome back to the jet lagged session. And the last one would be René. And so I'm in the third position, so many things have already been told. I will try not to destroy René's talk this afternoon. And add some things and some more pictures. And so I have to thank my two preceding colleagues for giving all the words and theorems and so on, so I can be quick about some points. So I also changed my title, sorry, it evolved, says something between 4 and 5 this morning. And so I decided finally to put computations instead of perspectives, which is far away from what I want to talk to you about. And after that, after all, my only interest is numbers. So history is good, numbers are good. And perspectives, you'll see. I put some of them on my slides anyway. And I also put some exercises for you. Probably much easier than what Gerhard Frey suggested. I don't know where you can find students that can do that in their first year. But anyway, at least not mine. I mean, I will try next week, but pretty sure it won't go. Okay, so a little bit of history, classical theorems, what I call a new era, whatever. And I will insist on doing old things and new things about modular curves and class invariants. Okay, history. I have nothing to say really about history because so many people worked on that theory, but I don't need to, I have no time, in fact, to remember everything, to remind everything. So just adding that apparently Gauss was also the inventor of complex multiplication, but since he invented so many things, okay, anyway, it's Gauss. And so I did here a very good book presenting the theory and history of early attempts and computations and theory about complex multiplication. And you already heard the name Kroneker's Jugendtraum. And this is good reading. So sometimes he forgets some names here and there, but anyway, a good lecture. A good reading. Okay, a new era. So it begins with Renaissance. For me, at least, it begins in 85. I guess it's why we are here, 25 later. And he gave this first polynomial time deterministic algorithm, blah, blah, blah. And so now I have a question to ask you. When was the last time you read that paper? So yeah, you see, I was with that old piece of talks. And so I decided to protect very important papers. So like the ESTA form to get here. And another very important paper is this one. This is my own copy of Renaissance algorithm. You see it's very, since I had to read it a lot of times, it's written, and I've got some corrections also, but everybody knows how to correct a paper, and I had to staple it once or more. So, okay, when was the last time you read that paper? Never did? Bad thing. You should always read the master's papers. I think what's the exact saying? I cannot remember, but something like this. So, okay. And you already heard this story about marketing and so on, so I don't have to comment on this. And so the marketing point was here to compute that problem, which seems a bit easy, compute the square root of 1 mod p. So you can do that in many cases and very easily. But you need something deterministic. And as you know, computing square roots mod p might involve some quadratic known residue, and that's not deterministic, at least at the time of today. And so probably you do not remember that this is the first paper that introduces CM techniques, in fact. If you read carefully that paper, then you don't need to learn the other papers. Everything is in there. In a kind of strange way, because to reach that goal, you have to start from an elliptic curve with complex multiplication. You have to build it, and after that, you get the square root. And primality proving with CM theory is just the reverse, kind of transposition principle. So everything is in there. Took me quite some years to agree on this, but everything is there. So this is another reason why you should read it. So history again. So you already heard many versions of this history, and I can maybe I'm wrong in the years here, not here but here. So ECM, we already see this, we already saw this. So here I insist on the precursors, so to speak, of primality proving. The first attempt was done by V. Bosma in his master thesis, I guess, where he used special primes in Z of I and Z of rho, which is kind of ancestor of, the first two cases of CM primes. And at the same time, Shunovsky brothers write an IBM report starting from ECM or things like this, and try to list a long list of collection of possible parametrizations of elliptic curves, looking for one that would give ECM, a fast ECM or something like this. So this report was not available very easily at that time. Finally, it went in print in 1987. So primality proving, I see this as two independent threads. On the one hand, Atkin said, okay, let's try to use CM curves to actually prove the primality of real numbers. And the second thread is, okay, can we use elliptic curves to get that primality proving is in RP? So for elliptic curves, it cannot work because we need some very deep, precise analytic number theory theorem, which is still a conjecture, but obviously true. And it does work if you use hyperelliptic curves of genus 2 and corresponding CM properties, which was done by Edelman and Wang. So, and here, okay, so I should put this a long time ago, apparently, if I follow Victor's presentation. So I will stick to primality proving in the rest of my talk. So suppose I want to do some ECC. At this point, you have two methods. The first one is take a curve at random and wait for the curve to have good properties, which means that you have to compute its cardinality and all other properties like being smooth or not smooth or whatever. But the problem with Schoof algorithms, and its improvements is that at the beginning it was rather slow to implement and almost impossible to make run on elliptic curve cryptographic sizes. Or you can build E as a reduction of some CM curve. If provided you can do that, you have properties here. And it's easy. We will see that computing the cardinality of E is trivial if it has small CM. But then you are not sure that your curve here is good. Maybe if it has small CM, then it could be endangered by some unknown properties or something that we did not use yet. Anyway, CM curves are the only way of dealing with problems like computing or finding pairing friendly curves or things like this. But still we have, for I mean, in these 25 years, we still have this dichotomy. Here, Raver's law could be made rather fast, if you want, or faster. Here, you have the same problems again. So we still have two threads. Here, I will concentrate on the second one, and most probably, René will comment on this part. So we need theorems to go a little further than what Professor Fry told us. So everything is related to properties of imaginary quadratic fields and orders of discriminant D there. So I remind you that ring of integers can be generated by some omega here, quadratic integer. Class number would be H of O, and the class group of O will be denoted by CL of O. Typical example, D is -4, K is Q of I, ZK is 1I, class group is trivial, and class number, of course, is 1. And one of the most important theorems in CM theory can be summarized here. You can represent the prime number P as a sum of squares, so to speak, if and only if P splits in the Hilbert class thing KD. And the easy case, so to speak, is a case where the conductor is 1 when you hit the Hilbert class field. How do you build this guy? The second important theorem is that you can build it using a singular value of the modular invariant J, where J is defined maybe by this series with some very precise coefficients here. So in theory, you can solve this problem by solving this problem, for instance. So we'll try to, I will spend some time explaining how to build this in an efficient way, and one day we'll see the relationship with elliptic curves. Okay, more on the Galois theory of this guy, KD over K. It's a Galois extension, and the Galois group is isomorphic to the class group, CL of O. And as a result, the degree of the extension is the class number of O. And we have an explicit Galois action that we can use if we want to do that. The minimal polynomial of J of any element of the class group is just a product of all these factors. And it happens that this polynomial has coefficients in Z, which is a very important point if you want to do computations. If you land somewhere in Q, then it's kind of boring because you need something. You need to know something about denominators, and here you are really on integers. And so if I just rewrite one of the preceding theorems, then this equation is satisfiable if and only if P splits mod D. Sorry, if P splits in the Q of square root of D, which is a necessary condition, and HD of X, this polynomial, has HO roots mod P. So the trivial example, which can be proven with other techniques, is that 4P can be written as a sum of squares. Here, this is a real square, if and only if P is 2 or P congruent to 1 mod 4. Good references for this, the old lecture notes in math number 21. When was the last time, blah, blah, blah? Nobody. Okay. Sales book, Cox, Cohn, etc., etc. So everything is in there. And everybody should read everything, anyway. I could put also Weber and Fricke, but this is for following slides. Okay, how do you compute this? That's very easy. You compute your class group. So, okay, D is small. Class group is easy to compute. So you represent all your ideals in the class group like this, and you evaluate J of alpha 1 over alpha 2 as a multi-precision number. So since we are not afraid of complex multiplication of floating point numbers, it works well. We compute the first values, class number 1, not very interesting. More interesting, H of minus 23 is this guy, and this is a case of of order with conductor, non-trivial conductor, sorry. You have these big guys. So you recover again my theorems about writing P as a sum of squares. And here you have a condition for 4P to be written as this sum of quadratics and coefficients, if and only if this condition is satisfied and that polynomial splits mod P. And so immediately you can see that we are not happy with big numbers like this. And so a large part of progress in that was to, or has been to, reduce the coefficients of this. So probably it's time to introduce elliptic curves at some point. So you already saw that we spoke about elliptic curves and their complex analytic representation. Then that's easy. You look at the endomorphism ring of E, and Professor Fry already told us about all possibilities. And we are interested here in cases where the elliptic curve has endomorphism ring greater than Z. And the fundamental theorem already given to you was that the only possibility is that the endomorphism ring is a quadratic order in some imaginary quadratic K. Trivial example, E with this equation has Cm by Z of I. Always the same thing. And if I collapse, or if I collect all my theorems until now, then I say E over C as Cm, if and only if its invariant, G of A, is a root of some class polynomial, Hd of x, for some D. And obviously, this is completely non-effective. And what we do, generally speaking, is that we take some Hd of x, compute a root, and deduce A. This is the way we are going to work with it. What happens over finite fields? Hasse and Doering have already been cited. And Hasse's theorem tells you something on the cardinality. And everything is contained in Doering's work, where it tells you that there's correspondence between reduction of elliptic curves mod P and the set of elliptic curves defined over Fp. And in theory, it's possible to start from T here and find the curve E here over the extension KD and reduce it and get an equation for the elliptic curve E here with that cardinality here. So theory tells you that you can do that. Practice tells you that you cannot. Or more precisely, if you look at this, it's not really effective, or it is, but you see you have to compute this guy here. And if you take a random elliptic curve here, this guy is big. So these guys are big. And so big meaning, I don't know, exponential in log P. And computing the class polynomial will be infeasible. And so we cannot do it. At least we have no method to do it right now. So these are at the same time good news and bad news. Good news because we have a bound on the cardinality of E. As already said, each time you make T vary, you get another group. So you have plenty of groups. If you have plenty of groups, you are happy because you can do factorization and primality proving. We'll see that in a moment. Bad news is that given E, it's difficult to compute its cardinality, or you have to use a Schoof algorithm. And everything I told here can be generalized, except maybe on some traces here, but everything is known. Okay, so we have everything we need to understand Schoof algorithm, the marketing point, and I hope maybe we can improve it a little bit. So how do you compute square root of -1? That's very easy. You take my curve, y squared is x to the third plus x. You compute its cardinality using Schoof's algorithm. That can be done in deterministic polynomial time. And then theory tells you that, in fact, this cardinality you have computed is necessarily of the form p plus 1 minus 2u, where p is u squared plus v squared. So now that's easy. You know the cardinality. You deduce u. You deduce v, because extracting the square root of an integer is easy. Deterministic polynomial? No, just kidding. That's true. But This is not a difficult point. And from that, you get square root of minus 1 mod p. That's marketing, but that's beautiful. Sometimes marketing can be good. Sometimes not. But anyway. And I claim I can improve this a little bit, this complexity to this. So now specialists know approximately what will happen. What is this complexity here? No specialists in the room? Surprising, to say the least. So this is the complexity of the improvements of Elkis and Atkin to the basic algorithm. So what do I need? Waiting. OK. I need eigenfactors of my division polynomial. Never thought about this? That's funny. OK, here it is. I mean, we are not dealing with ordinary elliptic curves. We are dealing with CM curves, and we know everything about CM curves. In particular, we know exactly when the division polynomial FL, so that's a new object. You will hear more properties later. And this guy codes the abscissa of points of order L. And so you can be sure that in any of my talks, P is a prime, L is a prime. And sometimes they can be equal, but I mean, this is a prime. So everybody knows that primes congruent to 3 mod 4 do not split in Q of I. And in fact, if you look at FL, it's irreducible over Q of I. On the contrary, if L splits mod 4, then FL has two. So I use that term eigenfactor for a reason that will be clear in 5 minutes. And in particular, you can factor your FL as a product of 2 degree L minus 1 over 2 polynomials with coefficients over Q of E, and some guy here which happens to be irreducible. And you have many more properties, like here you have only even powers here, and that's very funny to play with this guy. So what's the idea now? I compute this over Q of I, and now I'm looking for what happens mod L. I'll work in this ugly-looking extension. Remember, I know that I exist mod P. Okay? So this is not a finite field by very far. So this is the ordinary stuff when we work over with eigenfactors in the C algorithm, and I added here this extension. So this is not an extension. You're looking for a root of this. So I can run the Schoof algorithm. I find the eigenvalue here modulo this eigenfactor here. And if I've got enough answers like this, then I can use the Chinese remaining theorem to get my trace mod enough small primes. And now I've done the same thing as the C algorithm. I'm working over polynomials here of degree L minus 1 over 2. OK, there's a slight overhead working in this. But still, this gives a good complexity. Now, how do I compute these guys? Because obviously, I don't want to compute FL, factor them. That's stupid. OK, that's deterministic, blah, blah, blah. No, not deterministic anyway. But it's not fast. So the next ingredient is to use what are called generalized division polynomials. In fact, we can define polynomials, division polynomials of integer indices. This is a classical way. But you can do that also for complex indices there. And more precisely, in each case where E has Cm. So here, what I want to do really is to write my polynomial here, maybe this one, as a sum f of a complex index, and it's precisely f2 plus I. And Sato gave a long list of recurrence relations for computing all these guys. And you have, if you ever encountered division polynomials, you know that there are a bunch of equations like this. And there's another bunch here. But you can do that in polynomial time, and that's OK. After that, you have to be a little careful because we are working in that non-extension. So equality testing is not comparing objects. It's computing some GCD here. Every time you have to compute some equality, you have to test equality of coefficients by computing GCD. And it works. For instance, take this example of P is 241. So everybody knows that prime congruent to 1 mod 8 are the most difficult guys to compute square roots in the finite field. So my f here is this polynomial here, when reduced mod p. I compute the action of the Frobenius. This is it. And so you realize that lambda is 1 mod 5. It should be minus 1, sorry. Anyway. But what is strange here is that, in fact, you don't really need this extension of Schoof algorithm for kind of bizarre reason, is that here it's definitely not an extension. So what happens some very, very, very often, almost always, is that you can discover square root of minus 1 during the computations. For instance, here I told you that you have to compute x to the p squared, y to the p squared modulo this polynomial. Sometimes you have situations like this, like yp is some random number times y. So if you raise it to the power p here, you have x to the p to the squared is plus or minus y, which means that this guy is the square root of minus y. And so in all the cases I tried, I always found square root of minus 1 well before the bound given by the theorem. So this is not a proof. I'm not sure I can prove it, but that's fun. OK. Let's move to the next topic. So you already saw many pictures of many people, and so this is a real-life picture, and more interesting that people posing like, OK, I'm etc. So this is a dog, by the way. And so it's time also to put some citations. So that's a mail I received a long time ago, 88. Most of you were not here. And so you see, working with Atkin was kind of interesting in many aspects. And one of the aspects was to learn English. And the importance of being very precise in using words, like implementing. So I'd better not say I implement or blah, blah, blah. Or anyway. And something like the difference between perhaps and maybe. And things like this. So this is very important for when you try to learn that language. Anyway, the idea of Atkin was kind of using all the ideas, just changing, he called that changing power supply or power energy, like replacing, creating electricity out of coal by using atomic energy or something like this. So you just do the classical thing like the converse of Fermat's theorem. Like, OK, if I can factor n minus 1, then I can prove the primality of n. And so the idea was just using the same scheme and instantiating it with other things being elliptic curves with Cl. And so the inner loop of ECPP from very far away from hyperspace is something like this, recursive algorithm. You try to represent n as this quadratic partition here. If you can succeed in doing that and this number factors in some way, then you are more or less, if n is prime, you are creating the cardinality of an elliptic curve mod n. And if n is prime, then this curve has order m. So you just have to find a proof that it is an elliptic curve having a point of order m. You can build the curve with techniques related to class fields and so on. And that's it. And you just have to prove recursively the primality of the cofactor. And this is not an algorithm until I explain you or until I give you a precise definition of this set of fundamental discriminants. In fact, it's a meta-algorithm. You can highly depends on D here and many factorization parameters and so on and so on. The basic thing to do is to take the set D as the set of all discriminants which have size bounded by log n squared. And after that, you do some analysis, and you realize that you need log squared discriminant before one of them will give you some splitting, good splitting. And this costs you the cost of computing square root of D mod n, which is asymptotically this. And you have to do a recursive proof of this length. And when you add everything here, you end up with a running time of O tilde of log n to the fifth. And this is really the dominant step here, and all other steps will have this complexity. So this analysis was done by Lenstra and Lenstra in 1990 in the handbook of complexity theory or whatever, computer science maybe. So I must say that Atkin was not very interested in that part. I was not either at that time. We were more interested in proving numbers to be prime than to which complexity we could reach. That's a mistake, okay. But that's life.
This is probabilistic, right? It's not deterministic.
Yeah, sure. I never said it's deterministic. So I insist, this is probabilistic. I mean, the analysis is completely heuristic in particular. So this is a kind of a polite way to say hand waving. Hand waving. Sorry. Okay, and what you gain at the end is a generalized Pratt certificate, if you insist. It has size log n squared, because you have log n steps, and each step comprises log n numbers. And if you want to check the certificate once we have spent all our life doing this, is log n to the third. So as usual, O tilde means we count, we use fast methods to do multiplication. Okay, short history. So, it's very difficult for me to do history on things I do. And as a matter of fact, this is why there are people doing history. You are not supposed to do the history of what you did because it's a kind of endless loop. So just some facts. Atkin did some primality proving of numbers in the Cunningham tables. I mean, the largest one at that time. If I remember correctly, this was 243 decimal digits. At that time, the program by Klein and Lenstra using Jacobi sums was able to do numbers up to 150, 200 decimal digits. So Atkin went a little further. I did some things with larger numbers, cofactor of F11, and then I distributed the computations among other things, and in that way I was able to do 1,000 decimal digits. So the remaining problems at that time were class polynomials, because it was apparent that going further would need more small invariants. There was some competition by Marcel Martin and his program Primo, which runs only on non-Linux stuff, so to speak. And in fact, it was a kind of sleeping because nobody cares about primality proving. So that's a fact of life, except for some stupid numbers like Cunningham numbers or whatever. So we spend all our life doing clever algorithms, and it ends up on Cunningham numbers. As far as primality proving is concerned, of course. No. Okay, and then there was this controversy with Dan. It's always, it's kind of tautology to have controversies with Dan. But he said imprecise things on the exact complexity of ACPP. So I told him there was a faster method that nobody tried because we didn't care, in fact. And so to make things clearer, I had to write the program myself to show that it was indeed fast. And in fact, when you look at it, you just replace your set of discriminants by some products of small discriminants. And the idea is that you reduce the complexity of the square root finding by this trick. So now everybody works in O tilde of log n to the 4, and we were able to do many things like 10,000 decimal digits, 15,000, and 20,000. So now everybody can guess what will be the next slide.
The picture of done.
Sorry?
The picture of done.
What?
A picture of dance.
No, everybody knows Dan is... Who doesn't know Dan? It would have been more fun that Tanya answered that. Okay, anyway. Okay, so of course I cannot come here without a new record. And you see this is like numerology. That's very easy. You find a size. So you see 25, 0, 50. Because this is the 25th anniversary. Sleepy or hungry? And I just managed to do that just before coming, which was actually nice. But I mean, it's not really fun because it's a polynomial time algorithm. And you know the complexity, so you know the time it takes, in theory. And after that, you have to have some idle machines and blah, 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 blah. So in the event, I'm still alive 25 years from now, I will do 50, 0, 25. So since the organizers of ECC, whatever, 2035 are certainly in the audience, you can count on me if I'm still alive. I mean, meaning with a brain also. Otherwise, okay. Otherwise, I will tell you that I have proven the Riemann hypothesis or something like that, which would be embarrassing for you. Not for me, because without a brain, I cannot realize that's true, you know. Okay, so some details if you insist, and these are CPU days. Blah, 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 GMP, bycore, whatever. And you see the time spent in the whole algorithm is dominated by the time it takes to check the pseudo-primality on the cofactors at each step, which is a kind of silly thing. So computing class polynomials is here. It takes no time. So I did not need the help of Andreas or Andrew Sutherland, Andreas Enge. I was able to do that myself with my old program. And you see that step 1 takes some time. Step 2 also. Checking the certificate is just 4 days, 4.5 days. Okay, so everything is okay with primality proving. I push a button and I leave, and now I can do theory. This is the advantage of computers. They do what you don't want to do, and they do not complain, and blah, blah, blah. Contrary to many people's. Anyway. Okay, so what happened? Contrary to other primality proving algorithms, you can extract the real important piece of it is constructing elliptic curves. Because as I already told you, nobody cares about primality proving, but some people care about this, building curves with CM, because then I can meet some properties I want to do serious things like ECC. So I did some paper here explaining that we can build cyclic elliptic curves with this. It was answering a conjecture by Kaliski, already cited. Absolutely, I guess, no interest anymore. You can make some other parameters vary. So we tend to fix E and fix P and vary E, but you can do the other way around. So that's Renier and Peter, which is there. You can do pairing-friendly curves. I'm pretty sure we have a talk on pairings at some point. And you can use also that in EKS, which is the elliptic analog of KS. So this is very important. This is a primitive that we extracted from our problem. So now ECPP can die. We have still this primitive around, and it's OK. So I just want to insist on a slightly different context. Why is that? In primality proving, we are dealing with very big numbers. real stuff, very far away from crypto applications. But we don't care. This is a number theory, you know, numbers. It's not supposed to be useful, you know. So, but it's full of math, and that's easy. No, that's not easy, but that's fun. Blah, 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 blah. And compared to this, cryptography, you need very small primes. But here you know that P is a prime. Maybe it was proven by ECPP, but that's another story. So here it's probably, so there are some differences. Here maybe you are not satisfied with all discriminants. Here we take all discriminants. And here you want maybe some cardinality which is prime, which has some impact on this. And here certainly we do not want our curve to have a prime order. Otherwise you enter an infinite loop. Yeah, I can assure you. And here nobody cares about checking my certificates. So maybe they are wrong. No, they are not. But nobody checks. So I can send all I want. Here maybe you could dream of having people verifying certificates. Maybe. But maybe not. But in both cases, you have to deal with big Ds and big class numbers. When did I start it? When did I start? 10 minutes too. Oh, plenty of time. Great. OK, so what is the CM method? This is an approximation of the CM method. Input P, maybe a finite field here, more general finite field, and UNV such that this output a curve which has this cardinality. Here I had a proof of correctness because sometimes you want to do neat things. Here I put U and V in the inputs. If they are not, I can add them and blah, blah, blah. Proof of correctness. This is the tricky part. Maybe I do not, I mean, for primality proving, the proof of correctness is the proof of the next step. Okay. In CM stuff, you have to prove that this number is actually the cardinality of that curve, which might involve factoring M. And everybody knows that factoring is difficult. So there are many tricks here, okay, to speed up things. That's not deterministic, but you can be rather confident that this condition is satisfied. In fact, you have to exhibit generators. And exhibiting generators, as Victor Miller told you, might involve some pairings. And after that, where do you find the generators? That's far from deterministic. So a more precise version of the same thing is now the output. I want E to have CM by the order I gave. Here you can find some methods where you find a curve which has this cardinality, but maybe it has nothing to do with here the good endomorphism ring. If you don't care, that's okay. If you do care, then you have to prove that E has this endomorphism ring. And this might not be very easy, depending on the size and factorization of the conductor. But these are two precise things about the CM method. You can find variants and so on. So how do you work in practice? So this is a basic skeleton. You have to compute this class polynomial, or have it on some disk, whatever. Find the root mod P, find the curve of this invariant, and prove that the cardinality is OK. So computing HD of x, now we can do that in big O of D1 plus epsilon. I won't say anything about this. You have to wait for Andreas's talk. Find the root of HD J of x. This is a computer algebra technique, so everybody knows everything. Atkin did some interesting things about this, speeds up and so on. You can try to spend all your life finding the right curve here. This needs generally long, very interesting math. There's quite a long history about this. The last step was done by Rubin and Silverberg when using the J invariant. So there's a kind of there are formulas for given all this and J, we can find the right twist here. So there's still some work to be done when you do not use J, because we never use J for large examples. I can do that in some cases, but it's not completely satisfactory. And after that, you can spend quite a lot of time trying to find adequate parametrizations and so on and so on. So this is all you need to build a curve with CM. Here I did not list things about proof, correctness, and so on, and not the volcano stuff either. So I want to conclude my talk by this last part, trying to put numbers everywhere and concentrate on this problem. How do I find smaller polynomials for building my extension field KD? And here again, there are two cases. First one, I just want an equation for my Hilbert class field or whatever. So probably you just need a generator of the extension field, and you can have some minimal polynomial. It can be very small, for instance, using units, elliptic units, and things like this. So I refer for this to Edgier and so on. And basically, you do not have to relate this to any elliptic curve. Or you are trying to build a CM elliptic curve, and at some point you have to have its invariant J. So you have to find a relation between your minimal element and J, and instantly this means modular curves, so to speak. So this is the traditional ancestral way of dealing with the class invariance. You start from some known value of some singular modulus, J of square root of minus 2, and you plug it in this, which is a modular equation for x0 of 2, and that's kind of miracle. It factors, and you find roots which are rationals. And everybody knows that 64 is less than 8,000, so you found a smaller invariant. And so all the game here is to generalize this, have long lists of modular equations and modular functions, and so on and so on. So very briefly, sometimes I put the 0 upstairs and sometimes downstairs, but I mean, they are isomorphic or whatever. So a modular function is something invariant by these guys here. And the modular function is what? You take the minimal polynomial of this function applied to these cosets. I don't really need this, but at some point you have to define things. So why do these invariants exist? Because you see, I take a random equation at random, this one. Why would it split? Okay. So what is obvious is that if J of tau is an algebraic integer, so it is f the tau. And in fact, the theory tells you that if you manage to find one guy, f of z, which is in KD, and sorry, this is a goal we want to reach, sorry. If we know that fz is in KD and is conjugate also, we are done. And in fact, everything relies on Shimoda's reciprocity law, which tells you when this precisely occurs. And you have at least two variants of Shimoda's reciprocity law. And we prefer to use Schert's simplified formulation because we can apply it to families of functions, basically. So how can we measure that we have a good invariant? There is this theory by Hendry and Silverman telling you that if f and j are roots of bivariate equations, the ratio of heights is more or less the same thing as the ratio of the degrees of the two variables. And what you want is a constant here which is as small as possible. Because you see, you want something here which is much smaller than this guy here. So that's easy now. You take modular functions on some gamma 0 of n, you compute a magical constant, and when you have it, you are happy if it's strictly smaller than 1. And things, since it can be proven that, I mean, we have a formula for the genus of x0 of n. In fact, this genus is more or less mu0 of n divided by 12, which means that asymptotically, in a very, very, very broad sense, this constant tends to 1 over 12. But we have many cases where we can do better. I mean, when n is small, our special properties, we can do better than that. But we cannot dream, we cannot go asymptotically much better than 1/12. So, time for another citation, which is a bit puzzling the first time you read it. So when you're young, you're trying to read these on-verb things, and you find citations like this. And when you're interested in algorithms, then you are a bit astonished by algorithms. So since we have the offer of the citation here, so you see, okay, how can I implement luck? That's the first point. Theta functions, okay, why not? This is horrible, and this is the standard way nowadays, so to speak. So when can we be lucky? When we have nice families like eta quotients, as many people did, and including what we did recently with Andreas. We have an infinite family, for instance, for x0 of L to the n. Remember, 0 upstairs or downstairs is not very relevant. So we have many things, and we are trying to find algorithms out of this, and this is terrible. But there's one nice thing, is Newman's lemma, which tells you that some product of eta functions give you what you want. If you have luck, this is a kind of minimal function, so to speak, and you are happy. So you can do that for each case where the genus of x0 of n is 0, which means that degree in J is 1. In that case, magical constant is, so to speak, minimal as it can be, which is 1 over mu0 of n. You have these values for the invariant bizarre eta products. And these are particular cases given by Newman, but at least they were known to Klein and Fricke. And you see you have these magical constants here, and this guy has kind of record, this product of eta function, as the inverse of the magical constant equal to 36. So this is a table of invariants and their respective inverse of a magical constant. And there's a conjecture, so which comes from Selberg, Abramovich, and written in that language by Broker and Stephen Hagen, that you cannot do better than 96. We are far away from it. We have just 72, and we are cheating here a little bit. So, and I tried to find these better examples, but seems to resist. I mean, 48, there are not a lot of them. My table will be completed, no, not completed, but extended by Andreas in his talk. So you have really to go to his talk if you want to see what happens here. And you see we have many examples of 36, which means that we can use them in practical instances. So what we did with, what we are currently doing with my student Eric Brier, is to look at all examples where modular curves have quotients by subgroups of the Atkin-Lehner involutions, by one of the subgroups of the group of Atkin-Lehner involutions, which are more or less the same as the group of the automorphism of the curve, which have low genus. Why do we do this? Because you see, when you quotient a modular curve by some involution, then the resulting equation will have a degree in G multiplied by 2, but then you end up on a curve which can have a very small genus. And then you have to balance the increase here and the decrease here. And still, we have to find models of everything which are relating J to the appropriate function. So we cannot be satisfied with a minimal equation obtained by whatever means and not related to J. So we had to redo everything already done in the literature, so to speak, almost everything. So Fricke did a lot of computations. So that's a very neat book. You have, I don't know, 300 pages of theory and 200 pages of computations, which is what we like. It's kind of extension of Weber and so on and so on. And contrary to this, Hecke did not seem to like computations. I don't know if you agree. not very numerical. Anyway, and so the best we can do, I mean, this is history again. If we want to use the functions of, I mean, the minimal functions found by Atkin and his Landry method, then we end up with very good constants. For instance, for 71, x0 star of 71 has genus 0, and you have this good constant here, 36. So you see there's another citation I took in the paper written for the retirement of Atkin. And so everybody knows that I can be put in the list of others. So I'm quite happy or honored to be in the others. And it sent me a long time ago another way of looking at his minimal functions, because you see here the Landry method is kind of difficult method. And he wanted to prove that the functions were indeed functions. The best thing to do in that case is to recognize the functions as quotient of something everybody knows. So everybody knows about eta, the eta function. Probably, perhaps, not so many people are aware of this kind of generalized theta series. And I've got a long list of these minimal functions in terms of these generalized theta functions. And probably we should share these ideas, because there are many things I don't understand in that. So this is one of my first open problem, is should we do something about it? So yeah, okay, I should not write things downstairs. Okay, sorry. So I guess many people in this audience have received a lot of emails by Oliver. So maybe we could try to not to lose them and edit them in some ways. So if anybody agrees, we can try to do something. Because I can put everything on my web page, but probably it's not the best thing to do. Anyway, I can give these tables that are very useful for many reasons. So I'll be quick on that. The best paper on quotients of modular curves is certainly that by Gonzalez and Larios, when they give tables, precise tables, they are correct, and methods to find the equations in algorithmic, sufficiently algorithmic way. And also, they explain how to use intermediate quadratic fields predicted by Galois theory. So maybe I can show you the idea here on this big example. I start from x0 of 30. 30 has three different prime factors. So you can decompose, these are not extensions, but if you put q of x0, these are extensions. You quotient this curve by this involution, which is W15. You find a function here. So this is the lucky part again. You find this function for invariant and a good function for this guy here. And you quotient here by W3, and you end up on x0 star of 30. And each step here corresponds to a quadratic extension of the defining extension here. Oops, sorry. And you see you have functions here which are invariants. And in fact, if you put everything together, then you have this extension which splits over these three quadratic extensions. And this has the effect of decreasing the degree of the class polynomial. We will see that in a moment. Okay, so from the tables of Gonzalez and Larios, you have all examples where the genus of some quotient is 0. And I put here some of the results. And these are indices of Atkin-Ehner's involutions and the corresponding magical functions. So you see that you can have 36, 36 here. You have 24, 27 here. So they are not so bad. So this is just for genus 0. So you can you have still somewhere for doing over genuses, over genera, but probably it's not worth it. So again, lots of examples. Maybe this one. No, not this one. Okay, this one. For instance, yesterday in the plane. Why not? I imitated what Atkin did with these theta functions, and in fact, for 95 and 119, I could find some generalized theta functions which give the Hauptmodul for these two cases. And you see there's kind of family here. Everybody is congruent to 23 mod 24. 40, 23, you have this. 47, you have this. And probably for other cases here, you have the same kind of result. But, I mean, the plan took a lot of time, but not enough time for me to end the list. So, many other things. Summary of results. What we obtained is that we looked at all the interesting quotients. We still have some problems identifying known functions, but I mean, I'm rather confident we will do that. And from this and the splitting in quadratic extensions, you have cases where your class polynomials here have very strange properties. And Andreas, I guess, will give you other examples with eta quotients. And for instance, look at this example, 60, discriminant 660 is divisible by 110, and the class polynomial is an 8 power. So we have plenty of computations around here, and that's what is important. Open problem for complexity reasons and for practical reasons. Some of you might know that we can evaluate classical theta functions very rapidly, which means O of m of n, where m is the time to multiply two n-bit integers. And the corresponding question, can we evaluate a generalized theta function rapidly? I have no clue about this, so that's an exercise for you. This is the interest of being an invited speaker. I ask you questions and you're supposed to give answers. And exercises. And that's it. So this is a perspective slide. Okay, so after the 200 years of study, we have some satisfactory results. We have beautiful numbers and equations, which is the important thing, at least in my mind, and I'm almost sure in Atkin's mind also, and of many people in the community. What remains to be done, is of course the higher genus case, where you have very few results. This game of using modular equations to guess class invariance is very difficult, much more difficult because modular equations are difficult and there are many parameters. And you will have some talk about computing objects like this. And it's not as easy as what we have done in genus 1. So of course, I haven't told you everything on the subject. I probably forgot very important things. But I mean, these are most of the things I forgot to tell you about will certainly be described in the next talks. So you have to stay here until Friday night. Otherwise, you'll miss some important things. And thank you for your attention.
Questions for Francois?
I was wondering, for the very fast HD computation that you mentioned in your big example, how much slower would it have been to do a very naive J approach?
No clue. I can measure it for you if you insist. You're not supposed to say yes at that point, you know. Or you have to wait for some more sleep. I mean, I have to sleep before answering your question. I don't know. I will compute it for you. And you see, you have 200. You have 2,000 invariants. For this one, it took 5 days. For all these guys, it took approximately 5 days. I'm pretty sure in many cases I was able to have a constant like 30 or 36. So roughly speaking, I don't know, 10 days, 15 days, whatever. I mean, another way of answering the question is that not all cases are big. Okay, so now I can decide what is big, what is small. So I had the zillions of slides about sizes of invariants for the other cases, but I thought it was too much for today, so I will do that anyway. But I mean, invariants like Newman 18 and guys like this are very, very useful. And I'm not in the state of, I'm not in the state, but I'm not in the process of selecting my discriminants only based on this. Because for reasons I already explained, not so many numbers want to be smooth of that size. So you cannot be too restrictive about these. And obviously, if you want to do CM for crypto things, then probably a lot of invariants we suggest to use cannot be used because you want D prime, for instance, or not divisible by small numbers and so on and so on. But still, I mean, after that you can wait for Andreas, and he will give you a better answer, or Drew will give you a better answer. No?
I was just curious, in addressing Dan's question, it's not just the height factor, also the fact that you're getting these powers. I mean, you can take quadratic extensions.
Yes.
I mean, if you had a height factor of 36 and then you have an 8 power,
yeah,
that's a pretty big multiple. I mean,
yes. But unfortunately, my program ended before I was able to program this stuff. So, the problem with computers is that sometimes they do what you want. So, and I needed a plane to finish the computation. Anyway, yes?
Just to reassure you, by answering the very first question you asked, I did refer to René Schoof's thesis last week.
What was the question again? Oh, okay. Great.
Okay, so with that, I think we can thank the speaker again, and we're going to have lunch here.